Section: Introduction. In this section, we discuss the significant progress made in large language models, LLMs, that has led to improvements in agent-based planning systems. We categorize current agent learning methods into three types: direct imitation of actions, trial and error learning, and knowledge-augmented planning. However, we observe that these methods often resemble an unconscious pattern matching process. Agents learn planning skills by being exposed to explicit planning examples, which makes them vulnerable to unexpected inputs and can lead to failures in their decision-making. We note that while some advanced techniques introduce external feedback, they often do not address the agent's actual needs, resulting in inefficient learning. Excessive trial and error and indiscriminate use of knowledge can also increase the model's inference costs, making them impractical in real-world scenarios. In contrast, metacognition is a vital aspect of human decision-making, allowing us to evaluate our cognitive states and adjust our strategies based on changing circumstances. This ability helps us determine when to trust our skills, when to reflect, and when to seek additional information, ultimately improving our decision-making. Unfortunately, current language agents lack this metacognitive capability, leading to ineffective planning. We pose the question: can language agents develop situational awareness like humans? To address this, we introduce the concept of agentic knowledge, which refers to an agent's understanding of its ability to choose the right action based on the current environment. We propose KnowSelf, a data-driven approach that equips agent models with this knowledge, allowing them to selectively incorporate information based on their situational context. Our method involves enabling agents to explore their environment and classify situations into three categories: fast thinking, slow thinking, and knowledgeable thinking. We then create training data using special tokens to represent these situations. Our training process consists of two stages. First, we perform supervised fine-tuning to establish initial planning patterns, and then we apply a specific loss function to enhance the agent's capabilities. The agent indicates its situational awareness by generating special tokens, which facilitate selective reflection or knowledge incorporation during decision-making. We evaluate KnowSelf on two simulated agent planning datasets with different model sizes. Our experimental results demonstrate that KnowSelf outperforms various baseline methods with minimal reflection and knowledge use. Additionally, we analyze the scaling laws, generalization, and mechanisms behind agentic knowledge. In summary, our contributions include defining agentic knowledge, introducing KnowSelf for selective knowledge querying, and providing experimental evidence of its effectiveness. Section Summary. In this section, we discuss the limitations of current agent learning methods, which often lead to inefficient decision-making due to a lack of metacognitive abilities. We introduce the concept of agentic knowledgeable and our proposed method, KnowSelf, which enables agents to selectively incorporate knowledge based on situational awareness, enhancing their planning capabilities and performance in dynamic environments. Section: Method. In this section, we focus on constructing a knowledge system, prioritizing knowledge over the system's construction itself. We utilize a straightforward and effective method for knowledge collection to keep costs low. Our knowledge base is built offline and requires only a minimal number of completed trajectories. More details on this process can be found in the appendix. We define our final knowledge system as S, which consists of K, the knowledge base containing various forms of knowledge, and R, the module that selects knowledge based on the agent's past actions. Next, we establish a situation judgment criterion to classify the agent's situations into three types. We denote the agent's history as H_T, the correct next action as a_T+1, and the agent's predicted action as a_P_T+1. If the predicted action is wrong, the agent can rethink and produce a revised action, a_R_T+1. We categorize the situations as follows: I. Fast thinking, where the predicted action matches the correct action. E. Slow thinking, where the agent needs to rethink to arrive at the correct action. And E. Knowledgeable thinking, where the agent cannot determine the correct action and requires knowledge. This classification helps us create data for situation awareness, allowing agents to make their own judgments and reducing unnecessary training costs. We introduce a data-driven method called KnowSelf to enhance the agent's knowledge capabilities. For data construction, we take the history action pair, H_T, A_T plus 1, and use the situation criterion to create supervised data. If the agent predicts the correct action on the first try, we use that as the output. If the prediction is incorrect, the agent is prompted to rethink. If the revised action is correct, we mark this situation with a special token. If the revised action is still incorrect, we use the selection model R to find the appropriate knowledge from the knowledge base, marking this with another special token. After processing all input-output pairs, we compile our training data, D_self. For self-awareness learning, we implement a two-stage training process using this dataset. Initially, we train the agent with autoregressive loss to create a reference agent. Then, we allow this reference agent to explore the dataset and gather negative samples for a pairwise awareness dataset, D_pair. In the second stage, we introduce an offline objective to enhance performance and stabilize training by normalizing the loss based on output length. We also expand the model's vocabulary to accommodate new special tokens and analyze the effects of different training strategies in the appendix. Section Summary. In this section, we outline our method for constructing a knowledge system that efficiently utilizes minimal trajectories to build a knowledge base, denoted as S, sad face K, R, which includes various forms of knowledge. We also describe our situation judgment criteria for classifying agent actions into three types, guiding the development of self-awareness in agents through a data-driven approach called KnowSelf, which involves a two-stage training process to enhance their decision-making capabilities. Section: Self-Awareness Inference. In this section, we discuss self-awareness inference. During the inference process, if we stop after the first attempt, we directly add the predicted action to our history for the next decision. If we reflect after the first action, we continue the reflective process and include the reflected action in our history. If we generate knowledge directly, we select a piece of knowledge from our knowledge set and add it to the context, allowing us to proceed and then record the generated action for the next decision. We illustrate this process with an example in the figure. Next, we evaluate our method, KnowSelf, using two real-world simulated planning datasets, ALF World and WebShop. ALF World involves navigating a household environment and manipulating objects, with a binary reward indicating task completion. WebShop simulates an online shopping experience, providing rewards between 0 and 1 based on task completion levels. We use average reward as our final metric across all datasets, and our training trajectories come from Agentic. More details can be found in the appendix. We assess KnowSelf against two open-source models of different sizes, Gemma 2B and Llama 8B. To validate our approach, we compare it with various planning methods, including React, Reflection, ETO, and knowledge-augmented methods like Expel, KnowAgent, and WKM. We also include GPT-4o as a strong baseline. We introduce Know% to represent the ratio of knowledge-enhanced actions to total actions, and all prompt-based baselines are tested with two-shot examples. Additional baselines and reproduction details are available in the appendix. For training, we use a learning rate of 2 × 10 to the power of -5 and a batch size of 8 in the first stage, and a learning rate of 5 × 10 to the power of -7 with a batch size of 3 in the second stage. We set the beta in the DPO loss to 0.5 and the balanced factor alpha to 1, training for 3 epochs in the first stage and 1 in the second. We fix the temperature at 0 for all inferences, conducting our experiments on 8 NVIDIA A880G GPUs, with more details in the appendix. We compare our method with baselines that do not use knowledge. Our results show that KnowSelf consistently outperforms these baselines on both Llama-8B and Gemma 2B, with Gemma 2B even exceeding the performance of GPT-4o's React. Our Llama-8B model performs similarly to GPT-4o's reflection, which allows multiple attempts at a task, highlighting the significance of knowledge in agent planning. We also compare with knowledge-enhanced baselines to showcase the benefits of our approach. Our findings indicate that KnowSelf outperforms all baselines with full knowledge while using minimal knowledge. This suggests that not all knowledge is beneficial for agent planning. Interestingly, Gemma 2B's performance on Expel is worse than on React, indicating that too much knowledge can negatively affect weaker models. Notably, KnowSelf, with only about 15% and 17% knowledge rates on Llama-8B, surpasses GPT-4o's Expel on both datasets. Furthermore, KnowSelf performs better on ALF World with less knowledge on Llama-8B compared to Gemma 2B, supporting the idea that stronger models require less external knowledge. This demonstrates that enhancing an agent's knowledge can improve planning while reducing the need for extensive knowledge input, thus saving on training and inference costs. Section Summary. In this section, we describe the inference process of our KnowSelf agent, which incorporates reflective actions and knowledge selection to enhance decision-making. We evaluate KnowSelf on 2 real-world datasets, demonstrating its superior performance compared to various baselines, particularly highlighting that less knowledge can be more effective for stronger models, thereby optimizing training and inference costs. Section. Knowledgeable self-awareness is beneficial to break planning pattern overfitting. In this section, we discuss how knowledgeable self-awareness helps prevent overfitting in planning patterns. We illustrate the effects on the performance of our KnowSelf approach when we modify key steps. For instance, with ORET, means we exclude reflection, with OKnow, indicates we only use the model's reflective abilities, and, with OAll, shows we keep only fast thinking. We also create a scenario where knowledge is fully utilized, referred to as, with full know. Our findings reveal that training directly on ideal trajectories, with OAll, tends to lead to pattern fitting, while incorporating reflection and knowledge allows agents to plan more effectively. Notably, on both Llama-8B and Gemma 2B, just adding self-reflection, with OKnow, outperforms the addition of knowledge, with ORET. This suggests that agents often make correct decisions but are limited by their planning patterns. Furthermore, KnowSelf performs better than using full knowledge, with full know, even with a low knowledge rate, showing that too much knowledge can hinder performance, especially in weaker models. Thus, a careful approach to introducing knowledge is essential for enhancing agent planning. We also evaluate the generalization ability of KnowSelf using 3 simple tasks: put, clean, examine, in ALF World, and test it on 3 more challenging tasks: heat, cool, put 2. Our results show that the trained baselines suffer from significant overfitting, with ETO achieving only a 5.88% success rate on put 2 and no agent failing entirely. In contrast, KnowSelf demonstrates strong generalization, outperforming the best baseline, reflection, across all tasks. This indicates that KnowSelf effectively overcomes the traditional issues of training on specific trajectories, allowing the model to develop cross-task awareness and enhancing its ability to reflect and incorporate knowledge on new tasks. We also explore how the performance of KnowSelf improves with larger model sizes and more training data. We analyze data volume from both absolute and relative perspectives. When considering the total data as 100%, absolute refers to the randomly sampled portion for training, while relative includes common ideal trajectories added to this sample. Overall, Llama-8B consistently outperforms Gemma 2B, especially before training. However, after training, the performance difference narrows, suggesting that fine-tuning makes both models comparable. We observe that as the absolute data volume increases, performance improves, but when the relative proportion is below 40%, we see fluctuations or declines in performance. This may indicate that certain capabilities only emerge when the relative data exceeds 40%. Finally, we investigate how knowledgeable self-awareness develops in the last layers of agent models. We collect data on both fast and knowledgeable thinking from ALF World to understand how models decide to use knowledge during next token prediction. Our analysis shows that the probability of the reflection token remains at 0 due to a lack of slow thinking. Both the knowledge and action tokens appear in the final layers of the transformer for both Llama and Gemma models. This suggests that the decision to invoke external knowledge occurs only in the last hidden layers. Moreover, when the agent chooses to use knowledge, this decision happens even later, as the action token's probability can temporarily exceed that of the knowledge token before quickly declining. This process resembles a game-like scenario where the model's learned rewards guide its decision-making within the token space. Section Summary. In this section, we demonstrate that knowledgeable self-awareness enhances planning by reducing overfitting to patterns, as evidenced by KnowSelf's superior performance compared to other models, even with lower knowledge rates. We also explore the scaling effects of model size and training data volume, revealing that performance improves with increased data, particularly when the relative knowledge proportion exceeds 40%, while highlighting that knowledgeable decision-making occurs in the final layers of the model. Section. State-of-the-art reasoning models fall short in agentic knowledgeable self-awareness through only prompting. In this section, we discuss how current reasoning models do not adequately achieve self-aware knowledge through simple prompts. We have designed specific prompts to teach OpenAI O1 and DeepSeek R1 about agentic knowledge, testing them in ALF World and comparing their performance with KnowSelf. We present two examples to illustrate our findings. In the first case, O1 incorrectly uses knowledge without fully understanding it, leading to a mistake. KnowSelf, on the other hand, corrects this error through self-reflection, showing that having knowledge isn't always enough. In the second case, R1 chooses not to use knowledge and instead relies on self-belief, which still results in an incorrect action. In contrast, KnowSelf effectively avoids mistakes by using knowledge accurately. This highlights that in changing environments, an agent must understand its own abilities and adapt its decisions accordingly, which is the type of agent we aim to develop. However, we recognize that simply prompting the model is insufficient for developing these skills. We need to invest more in data, training methods, and model design to reach this objective. Regarding language agent planning, we note that large language models, LLMs, are becoming central to AI agents used in various fields like robotics, operating system manipulation, software engineering, and data science. Despite their success, these language agents face challenges in planning, such as generating incorrect plans or merely following existing patterns. Recent studies have introduced different types of knowledge to improve agent planning in relation to the environment, including symbolic workflows and constrained pipelines. However, many knowledgeable agents still inject knowledge through prompts or fine-tuning without considering the agent's own awareness. We also address situational awareness, SA, which is the understanding of an environment and its changes over time, crucial for effective decision-making. This concept has gained attention in fields like robotics and human-computer interaction. Recently, we have begun to explore whether LLMs can develop self-knowledge and enhance their situational awareness. To our knowledge, we are the first to identify the need for agentic design methods that improve the situational awareness of knowledgeable agents. Unlike the idea of knowledge boundaries, our focus on agentic knowledge emphasizes the importance of situational awareness in dynamic environments rather than just recognizing static facts.